Okay, so in this video, we will try to find a systematic way of representing familiar functions as power series. This will be a very informal presentation, and only later on we will look at a result called Taylor's theorem that will tell us what conditions a function must satisfy around a given real value in order to have a power series representation around this given real value. So then we will be able to prove that a given function has a power series representation around a given real value. But for the time being, we will assume that things do work out and see if we can come up with a formula for the coefficients of the power series for a given function. To simplify our discussion, we will assume that we are looking at a power series centered at 0. So suppose we have a familiar function f of x that is well behaved around 0, so we assume it does have a power series representation. So f of x is expressible as the series from 0 to infinity, Cn times x to the n. We can write out the first few terms of the series, so C0, the constant term, C1, multiple of x, C2x squared, C3x cubed, C4x4, and so forth. So here we assume that we have the special case where the center of the series x0 is equal to 0. The question is there a way to systematically find every given term of the power series expansion? As we're about to find out, the answer is yes. Now obviously, the coefficients of the series will depend on two things. One, the function itself, and two, the choice of center for the expansion. So we have f of x, and the idea is to repeatedly differentiate f, so finding the higher derivatives, and of course we will do so by using term-by-term differentiation of power series. So let me just rewrite f of x in its expanded form, then we'll start taking derivatives. So let's differentiate both sides, as both sides are equal as functions of x. This is our assumption. Keep in mind that the coefficients of the series, Cn, from 0 to infinity, these are constants, they are real numbers. So, when we differentiate the expression term by term, keep in mind that again these are simply constants. So the derivative of C0 is 0, as this is a constant, plus the derivative of C1x, this is a multiple of x, the derivative of x is 1, so we're left with C1, plus and so forth. So this will be, after we differentiate it, 2 C2 times x, plus this will be 3 C3x squared, plus 4 C4x cubed, and so forth. Well, if we differentiate the derivative, we will have, of course, the second derivative, which we can write as f double prime, or, in this fashion, without the parentheses in the exponent, this would be f squared, but with the 2 in parentheses, this means the second derivative of f of x. So let's differentiate now this new power series, again term by term. If we do so, well, the derivative of C1 is 0, as C1 is a constant, then we'll get 2C2 plus 3C3, the 2's coming down, so this will be 3 times 2C3 times x, plus 4 times 3C4 times x squared, and so forth. Let's differentiate again. This will give us the third derivative of f. The derivative of 2c2 is 0, as it is a constant. Then we'll get 3 times 2 times c3, plus 4 times 3 times 2c4 times x, and so forth. And let's differentiate one last time. And hopefully this will be enough to allow us to find a pattern. The derivative of this is 0 plus 4 times 3 times 2, c4 times 1. So 4 times 3 times 2 times c4 plus and so forth. And all the other terms would be multiples of x, x squared, and so forth. And now the idea is to evaluate each expression, f, first, second, third, fourth derivative, at x equals 0. And let's see what comes out. So if we replace x by 0, we will have that f of 0 is equal to, well, every multiple of x will be 0 as we are replacing x by 0, so these terms will vanish and we'll be left with c0. Let's do the same for f prime of x, replacing x by 0, f prime of 0. All multiples of x, x squared, and so forth will vanish, and we'll be left with c1. Replace x by 0 in the second derivative. All of these terms will be 0, except for the first term, the constant term, 2c2. Repeat for the third derivative. Third derivative at 0 will be, all of the higher order terms will be 0, except for the constant term again. So 3 times 2 times c3. Repeat for the fourth derivative. Replace x by 0. Will give us again the constant term. As all other terms would be multiples of x, x squared, and so forth, but once you replace x by 0, all those terms vanish. And now let's try to find a pattern. So we have the function at 0 gives us c0. The derivative at 0 gives us c1. The second derivative gives us 2c2. The third derivative gives us 3 times 2 times c3. The fourth derivative at 0 gives us 4 times 3 times 2, c4. So if you go back, there seems to be a factorial here. Think of 4 times 3 times 2 as 4 times 3 times 2 times 1. So this gives you 4 factorial times c4. Think of 3 times 2 being 3 times 2 times 1. So this ends up being 3 factorial c3. Think of 2 as 2 times 1. That is 2 factorial. This is 2 factorial c2. Well, think of c1 being 1 times c1, and 1 is 1 factorial. Think of c0 being 1 times c0, and by definition 1, or I should say 0 factorial, is equal to 1. And now hopefully you see the pattern. The fourth derivative at 0 is 4 factorial c4. The third derivative at 0 is 3 factorial c3. The second derivative at 0 is 2 factorial c2. The first derivative at 0 is 1 factorial c1. And here if you think of the derivative, well, how many times do we differentiate f to get f back? The answer is 0 times. If you differentiate f 0 times, you of course get f back. And so you see the 0th derivative of f at 0 gives us 0 factorial times c0. So hopefully now you see the pattern. So if you take the nth derivative of the function at 0, you will be left with n factorial times cn. And this is for all non-negative values of n. And so we have found the pattern now. If you think about it, the question was, can we find the coefficients of the expansion systematically in terms of the center of the series and f of x? Well, there we have it. All we have to do now is isolate for Cn, the nth coefficient of the power series representation of f of x, simply by dividing across by n factorial. And so Cn, the nth coefficient of the expansion, is the nth derivative of the function at 0 divided by n factorial. And there you have it. So now let's replace in the initial series expansion Cn for its formula, being the nth derivative of the function at 0 over n factorial. And so you see, to find the coefficients of a power series expansion for a function, all you must do is find the coefficients, at least where the center is 0, and evaluate all higher derivatives at 0, and divide by the index factorial. So the nth derivative at 0 over n factorial will give you the nth coefficient of the power series expansion of f of x, where the center is 0. So f of x, if it is nice enough around 0, will be expressible as a power series, and there's a formula for it. Cnx to the n, right? A general power series centered at 0. But here's the formula for the nth coefficient of the power series expansion. The nth derivative of the function at 0 over n factorial times x to the n. And we give this formula a very special name. We call this the Maclaurin series of f of x. And this was, of course, when the center was picked to be 0. But you can probably guess what will the formula look like if the center is x0 and we keep it as an arbitrary center of expansion. Instead of evaluating the nth derivative at 0, the special case, it will be the nth derivative at the arbitrary center x0. Of course, here this will be x minus x0 to the n. So if we try to now express f as a power series centered not at the special case 0, but at some other value x0, what we must do is evaluate higher derivatives of f, no longer at 0, but at this other choice of x, x0. And this is the so-called Taylor series of f of x centered at x0. And of course, you can see that the Maclaurin series is simply a special case of the general Taylor series when x0, the center of the expansion, is chosen to be equal to 0. So there you have it. If the function is nice enough, either around 0 or any other real value, it will have a power series representation, and we can find this representation systematically by evaluating the higher derivatives of the function at the center of the expansion. And that's it. But of course here, and I really want to close with this, we cheated just a little bit by assuming right off the bat that the function was expressible as a power series. Later on, we will look at, as I've said before, Taylor's theorem, which will tell us under what conditions it is possible to express a function as a power series. But the great thing is whenever this is possible, here's how you can find systematically the power series expansion around 0, namely the Maclaurin series, or a power series expansion around a different center, namely the Taylor series, centered at x0. And that's it.